Yeah, good evening guys. So please type in the chat box. Am I audible? So please type in the chat box. All clear? Great. Okay, so let us start this session. So yeah, all good evening Nitin. So in this session, we'll give introduction to gas power cycles like we have seen in, like I have told in yesterday's class. We'll talk about Stirling, Ericsson, and of course Carnot cycle also a bit, and then we'll straight away start with Berton cycle. But before that, we have left with one particular concept, which is regeneration in case of Rankine cycles. So we'll try to close that regeneration, and then we will move on to gas power cycles. Okay, so if you have a quick review of last lecture, we have seen Rankine cycle, and we have done the efficiency analysis. Okay, so thermal efficiency of Rankine cycle. Okay, so we have seen this. Then we have seen what are the methods for improving efficiency. Methods for improving efficiency. Okay, so methods for improving efficiency. So we have seen methods for improving efficiency. So we have looked at three methods. One is increasing pressure of boiler, and second one is decreasing pressure of condenser, and third one is increasing superheat. And also we have seen these two offer thermodynamic limitations, but whereas there is only metallurgical limitation here, so we have adopted this and we have done the cycle with slight superheating of the steam actually. Okay, and then after that we have also seen the concept of reheating of Rankine cycles. Concept of reheating in case of Rankine cycle. So concept of reheating is what we have seen. So we have seen there are two turbines eventually, and in between two turbines there is again one more heating which is going on, and because of this reheating we have understood mean temperature of heat addition. This is increasing, and as a result this increases the thermal efficiency. Okay, and W net is increasing, QS is also increasing. Okay, so and Dynamis fraction at exit. Okay, so at turbine exit, Dynamis fraction at turbine exit, this is also increasing. Okay, and load on the condenser, all these things increases. Okay, so specific steam consumption, if you see specific steam consumption, this will decrease in case of reheating. In last class we have seen how all these parameters are increasing, decreasing, how to decide on different things. Okay, so these are the things that we have discussed in last class. So are you all clear till this point? Yes or no? So please type in the chat box. Are you all clear till this point? Yes? Like these are the points. If you just wrap your notebook, you can see all these points just in last class. Okay, so we have seen these points. So I have given some homework yesterday. So let us, so reheating and superheating are same? No, reheating is different and superheating is different. Okay, see, I'll just tell you. If this is TS, let's say I'm heating a substance. Beyond this point, if I start heating, this is called superheating. Okay, so this part whichever is here is called superheating actually. Okay, so you convert complete liquid to vapor at this particular point. Okay, so at this point you have converted already complete liquid to vapor, but even further you're heating, that's called superheat. Okay, reheat is after one expansion you're again trying to do this. Okay, so that's what reheating. Okay, re is once again. Clear? That's the difference. Okay, Mudit? Got the difference? Normally any substance heating beyond its vapor state is called superheating, and heating multiple times is called reheating. Okay, fine. Now let's see, we have given some homework now. So of course in this lecture we will focus on feed water heaters and concept of regeneration in case of Berton, in case of this Rankine cycle. Then we will eventually go to gas power cycles, and we'll try to talk about some introduction to Berton cycle also in today's class. Okay, so let's see these two questions. Let us solve before we move forward. Did some of you solve these questions? Steam at 100 bar and 500 degrees Celsius, where enthalpy is at this state is this, enters a steam turbine that has one stage of reheat. Okay, so it has one stage of reheating. The steam is exhausted from the turbine at 0.7 bar and 85% dry. The net work developed by the turbine is 1600 kilojoules per kg of steam. Neglecting pump work, the heat supplied in the reheater is dash kilojoule per kg. Okay, so did anyone of you try this question? What's the answer? So please tell me the answer of this question. Did some of you try this? Did anyone of you try this question? Because I have left it in the PDF. No. Again today also no. Who bothers about homework? Next day anyhow Vanessa is there to solve, correct? No guys, but please make an attempt before I solve the question. Okay, I'm giving these questions not to show you that I can solve these questions. I can solve. I think you also believe me that I can solve. Okay, but I want you to think these questions before you solve. Okay, I mean before I solve it for you. Clear? Tried? Any one of you? No? Okay, you're trying now? Fine. Anyway, let us try to solve this question. Look, how many of you have this feeling? Anyhow, if you try or not, Vanessa is going to say solution tomorrow. So we'll, again write the solution then. So please try it, okay? Yeah, because in exam, I won't be there with you. You have to write your own exam. Clear? So that's why please make it a habit of practicing some questions. Okay? That's why I'm giving some homework daily. Clear? So anyway, let's solve these questions. So let's see. Steam at 100 bar and 500 degrees Celsius enters a steam turbine. So let's see. If you have a steam turbine generally, you have the TS like this, temperature and specific entropy, and you have the dome like this. Okay. Now let's see. There is a steam turbine and there is some expansion which is going in this steam turbine. Okay. After this there is some heating also. Let's see. So the steam turbine is like this. So this is state 1. This is state 1 and this is your state 2. Clear? So 1 to 2, there's an expansion in the steam turbine. Okay. Yeah, it's okay. But from today, whatever homework I give you, please try it. Okay. Like good boys. See here. So steam is entering at these conditions at 100 bar and also 500 degrees Celsius. So they have given you H1 value. H1 is equal to 3370.6 kilojoule per kg. Okay. So this is kilojoule per kg. Now steam enters the turbine that has one stage of reheat. So clearly there is some reheating which is going on. Let us change the color of heating. So let's say this is reheating. Clear? So this is reheating and there is some expansion to inside, maybe like this. Okay. So this is the expansion. It has one stage of reheating. So stage 3 and also stage 4, maybe somewhere here. So this is how the heating and of course the reheating and expansion is happening in the turbine. Okay. The steam is exhausted from the turbine at 0.7 bar and 85% dry. Means here, of course, I can just take the curve slightly away, far away. Okay, so let's say if I take the curve like this, then at this location, state 4, what they are telling you, dryness fraction is how much? 85% dry. So this is 0.85. And what about this pressure? Actually, this pressure is actually how much? 0.7 bar. 0.7 bar. 1 bar is equal to 100 pascals. 1 bar is equal to 100 kilopascals. So this is roughly 70 kilopascals. Okay. So this is roughly 70 kilopascals. Fine. And this is 100 bar. Okay. So the pressure at which this this state 1 is there, that is 100. Now the net work developed by the turbine is 1600 kilojoules per kg of steam. So W net is equal to 1600 kilojoules of work is generated per 1 kg of steam. Now clearly you can see if there is one stage reheating, the total network, okay, they have given you pump work can be neglected. Yes, neglecting pump work, because I told you the logic why you can neglect pump work in case of power cycles, because the energy consumed by the pump will be very, very small because of specific volume of the liquid being very small. Okay, so now if you see this W net, this implies this is per kg. So H1 minus H2 is produced in the high pressure stage plus H3 minus H4 is produced in the low pressure stage. Okay, so this is equal to 1600. Fine. Now neglecting pump work, the heat supplied in the reheater. So basically in the reheater, the heat supply is this process 2 to 3. Okay, and I told you in the reheater, if you want to calculate heat interaction between this point and this point, it's constant pressure heat addition. So nothing but the enthalpy difference between these two. Correct? So therefore H supplied in reheater is equal to H3 minus H2. This is what you want. Correct? So this is H3 minus H2. This is the reheating. Now you have this equation. Now you want this quantity H3 minus H2. Let us slightly arrange these terms. If you see, we have H1 minus H2 plus H3 minus H4 is equal to 1600. Now if you simplify this, if you spot this H1 and H4 as one term plus H3 minus H2 as 1600, this is equal to 1600. Now You want this quantity, what is this H3 minus H2? So for that, you should know what is H1. You also should know what is this H4. Okay, so H1 minus H4. Therefore, you can write one equation. H3 minus H2 is equal to 1600 minus H1 minus H4. Now, how you will calculate this? Let us see. H1 value, they have directly given 3373.6. So this value is 3373.6. The unit should be in kilojoule per kg. Yes, it is in kilojoule per kg. And what about H4? H4 actually. So 4 is this state. At this point, Dyna's fraction they have given you, which is 0.85. So H4 value is nothing but HF at 70 kilopascals or 0.7 bar. What they have given you, let us write that only as it is. 0.7 bar plus X into HFZ at 0.7 bar. Now they have given you these three values, correct? So you can clearly see HF at 0.7 bar. Here they have given at 0.7 bar, HF is 163.38. 163.38. The Dyna's fraction. What about the Dyna's fraction they have given? It's 85% high. So 0.85. And what about your HFZ? HFZ is also given 2409.2. 2409.2. Correct? So 2409.2. Correct. You punch these keys, then substitute this H4 here, you can get this value. So heat supplied in the reheater, is equal to certain kilojoules per kg. Okay, so this is certain kilojoules per kg. This is what you have. So let's do the calculations. Let us start from there. 2409.2 into 0.85. So this value plus 163.38. So 2211.2. 2211.2 kilojoule per kg. So this is nothing but your H4. If you substitute here, this value is nothing but 2211.2. That's it. Okay, so if you substitute, let's see, 2211.2, this has to be subtracted from 3373.6. This is the value 1162.4. Subtract it from 1600. So subtract it from 1600. 437.6. That's what you all are getting. H4 is 2211.2. Correct. It is 2211.2. This is 437.6. Correct. Yeah, all of you are correct. 437.6. 437.6 kilojoule per kg. That's it. Okay. So basically, what is the amount of heat supplied in the reheater? Once you understand the cycle, no need of mugging up any formula. Okay. So just follow your fundamentals. You all know heat added in a constant or heat interaction in a constant pressure process is nothing but change in enthalpies for a reversible process. Clear? That's what we have applied. 437.6 is the correct answer. Okay. 437.6 kilojoule per kg. That's what you have. Clear? So this is one question. Again, this question also can be solved with the help of what I have taught you. Let's see this question. In a power plant, water comes out of a boiler as saturated vapor at these conditions, and the water leaves the condenser at 0.08 bar and 40 degrees Celsius. Liquid water is again pumped through pump. Isentropic efficiency of the turbine. Yes, this word is a bit. Isentropic efficiency of the turbine is 70%. The plant has the capacity of producing 75 megawatts. The mass flow rate of the steam circulated in the circuit is dash kgs per second. Round off to 2 decimals and properties are given. Do you all understand how to solve this question? Come on, type it in the chat box. Can you all have some idea how to solve this question? Do you all know what is this isentropic efficiency? During entropy, I think Shivam sir might have taken you to this terminology: isentropic efficiency of compressors and turbines and pumps, of course. Yes. Have you heard this word, isentropic efficiency? Correct. So we all know. Like, let's see how do we define isentropic efficiency. If you have a pump, actually, or in general, if any curve is there, actually your ideal cycle has to be something like this. If this is TS, one, two, superheating. Okay, here they told it's heated only up to this point. Fine. Okay, 2 to 3. Then after, you expect it to be isentropic expansion, which is something like this. Okay, so this is actually, I think I have done isentropic already. Let me just keep this line straight. Fine. So this is your expected cycle. If you stop this point at saturated vapor state, because it's clearly given water comes out of the boiler as saturated vapor. Okay, so that means you're gonna stop at this point. So in actual case, we know process is not completely isentropic. Exactly. Okay, so this is the actual ideal cycle which you are supposed to have. But practically sometimes what happens in case of devices, because of heat loss, okay, normally even if you take any even if you take any turbine, practically there will be certain heat loss from the turbine. Okay, so it's not purely adiabatic, and also because of very high speed expansions, normally turbines operate at 80,000 90,000 rpm. At that high speeds, nothing is going to happen quasi-statically, so everything is irreversible. Okay, so that's why we define something called isentropic efficiency for the devices. Clear? So this expansion, and you know clearly if something is irreversible, instead of having this expansion, entropy definitely increases. Okay, entropy increases like this, and this point, instead of ending up at 4, it will extend something to 4 dash. So 4 dash 1 is your actual process which is happening in the condenser. Okay, so this is your 4 dash 1, and this process is not at all isentropic. In fact, entropy should increase actually along the expansion. Okay, because you may have one doubt, normally ds is equal to del q by t plus del s generation. You know this. Okay, now two things that happen is you can also ask me, this is negative and this is positive, how can you confirmly say that ds is definitely positive? That's the question you can ask me actually. Correct? Because it can be 0 also. I told you, irreversible heat rejection. This is exactly the case, and it can be 0 also. But practically in case of turbines, what happens is the temperatures at which you deal this gas will be definitely very high. So T is very high. T is very high actually. So this is very high, and this is del q. Del q, or basically the heat rejection happens because of losses, leakage losses. Okay, and actually the amount of heat you are putting into the turbine is some megajoules of heat. Okay, out of that megajoules, few kilojoules just get escaped because of leakage losses. So practically this del q is actually very small, and this ratio will be very small as compared to this in actual case. Okay, so that's why in all isentropic in case of all isentropic combustions or expansions, whatever, not isentropic, in actual cases entropy will actually increase, it won't decrease actually. Clear? Did you understand this point? Because of this, just from equations point of view, you may ask me, it can be 0, or maybe if this quantity is dominating, it can come this way also. But in actual case, because of the logics what I told you, this as entropy will actually increase as expected than this value. Clear to all of you? Now let's see if this is the case. Okay, they have given isentropic efficiency. Okay, so let us see what is this isentropic efficiency. Water leaves the condenser at 0.08 bar and 40 degrees Celsius. So this is the exit enthalpy of the water. So H is equal to 173.9. So H1, because this is the exit enthalpy of the condenser. Maybe it can be somewhere here also, we don't know, but this is the exit enthalpy. Okay, so this is H1. Now liquid water is again pumped through the pump. Isentropic efficiency of the turbine is 70%. Isentropic efficiency is 70%. What does this mean? Actually, turbine, let's say for example, if turbine is creating some 100 kilowatts of power, because of the irreversibility coming into picture, it is creating only 70 kilowatts of power. That's what it is, isentropic efficiency. Okay, so when there is some maximum capability of some engine or any device in general, the engine or the device do not work at its 100% efficiency because of this irreversibilities. Okay, so that's the deviation actually. So here if you see, the actual work which is produced by this turbine is H3 minus H4 dash. H3 minus H4 dash divided by H3 minus H4 is the actual work this is supposed to do. So this is 0.7. This ratio is 0.7. I hope you all know how to write this conversion factors by this time. Okay, because this is the actual work and this is the ideal. Okay, so minimum by maximum, this is 0.7. Now let's see. The power plant has the capacity of 75 megawatts. Okay, so it has capacity of 75 megawatts. So power is equal to 75 megawatts actually. Clear? It is generating a power of 75 megawatts. Mass flow rate of the steam circulated is dash. What is m dot s? This is what you have. Now clearly you know we know power is equal to m dot s into W net is equal to 75 megawatts. Okay, let us say 75 into 10 cube kilowatts, because we are generally habituated to write it in kilojoule per kg. Okay, now what is W net? That's the question. If W net is known, only single equation, single unknown, your question is done. Now how to calculate W net? W net is equal to work done by the turbine minus work done by the pump. So what is work done by the turbine? H3 minus H4 dash, which is actually 0.7 times of H3 minus H4, minus what is pump work? H2 minus H1. Okay, so H2 minus H1, this is actually the pump work. So this is what you have, because 1 is the condition at the outlet of the condenser. They have given you this. Okay, now let us see properties of steam. At P is equal to 0.08 bar, so at this location 0.08 bar, which is this pressure. So P is equal to 0.08 bar, roughly 8 kilopascals. Okay, you see such a low pressure. HF is equal to 173.9, which means we have drawn the diagram correctly. This 173.9 is nothing but the saturated liquid state. HFZ is 2403.2. SF is that value. SFG is this value. Okay, and at 72 bar, HG is this, SG is this. Pump work is 3 kilojoule per kg. Okay, pump work is given directly. Good. Pump work is given directly. So this value is 3 kilojoule per kg. Now only thing is H3 minus H4. H3 is nothing but Hg at what is this pressure? 72 bars. Okay, so this is at 72 bar. Fine. Now what about H4? That's what you have to identify. Okay, so H4 dash actually. Clear? So W net is work produced by the turbine, which is H3 minus. Okay, we have already multiplied 0.7. Okay, fine. It's okay. Fine. We can convert in terms of H4 better. Okay, so 0.7 times of H3 minus H4 because of this. Now how to calculate H4? That's the main question. So H4, if you see, this process 3 to 4 is actually isentropic, correct? So process 3 to 4 is isentropic. 4 and 4 dash are not on same line. No, this both has to be on the same line, correct? At constant pressure. Understood? Because condenser operating pressure is same. If the expansion is reversible or irreversible, condenser operating pressure is same in both the cases. Got it? So that's why it may increase, but it should stop on this line again. Understood? Any issues till this point? So please type in the chat box any issues till this point. Nitin, is the idea clear? But in temperature axis difference is same. Look, okay, we are dealing with steam, not ideal gas. Clear? If you try to do this in terms of CPDT, that's it, it's wrong. Clear? Because this is valid only for ideal gas. Okay, here things are not ideal gas. We are dealing in the vapor, steam and vapor. Okay, so that's why. Clear? So this cannot be used. Okay, now let's see. So H4. So how to calculate H4? H4 is equal to H1 plus Dynamis fraction at state 4 into HFZ. Correct? You know this. Of course, everything at 0.08 bar. Now H1 plus, how to calculate X4? That's the main story. This process 3 to 4 is isentropic. So clearly we know S3 is equal to S4 and S3 is equal to SG at this location. SG at 72 bar is equal to SF at 0.08 bar plus X4 into SFZ at 0.08 bar actually. Okay, you know this equation, just equating the specific entropy of state 3 and also state 4. Okay, now it is X4. If you use this equation, we have SG, this is at 0.08 bar plus SG at 72 minus SF at 0.08 divided by SFZ at 0.08. This complete value into HFZ at 0.08. That gives you the calculation for H4. Okay. सर मैं गेट 2025 के लिए प्रिपरेशन कर रहा हूँ सर, कितना रैंक सफिशिएंट होगा PSU में मिल जाए? I'll just tell you. Okay, just let us finish this question, we'll talk. Okay, so see here, in this case H1 at 0.08 bar plus this condition, and these values. Now the only thing is pick the values from this data and do the simplification. Let us do this. Let us do this. H4 calculation. So H4 is equal to HF at this location. So at 0.08, what is HF? 173.9. 173.9 plus. Now SG at 72. So what is SG at 72? At 72 bar, SG 5.8019. 5.8019 minus SF at 0.08. So at 0.08, what is SF? This value 0.5926. 0.5926. 0.5926 divided with SFZ at 0.08. SFZ at 0.08, 7.67. 7.637 into HFZ. So what is HFZ at 0.08? 0.08 HFZ 2403.2. 2403.2. This is your H4. So let us calculate this value. So if you calculate this, let us do 5.8019. 5.8019 minus 0.5926. 0.5926. This value divided by 7.67. 7.67. Okay, so this is the value multiplied with 2403.2. 2403.2. Okay, so 1639.25 plus 173.9 plus 173.9. So 1813.15. 1813.15 kilojoule per kg. So this is only the slight large calculation that is there here. H4 is here. Okay, so this is H4 1813.15. This calculation became easy because actually we have converted this H4 dash into H4. Practically using entropy relations, if you want to calculate the Dynamis fraction here, it would have been very difficult for you. Okay, so 1813.15, correct? Yeah, 1813. Yeah, correct. Okay, 1800 somewhere close to 1810 is fine. Okay, now this is what you have. What is H3? H3 HZ at 72. So HZ 2770.9. So 2770.9 kilojoule per kg. So this is what is the value of H3 here. Got it? So you got H3 and you simplified H4. That's it. This value is already known to you. Just put it here. You will get W net. Put it here. You will get mass flow rate of the steam. So let's do that. M dot S into now W net 0.7 times of H3 2770.9 minus 1813.15 plus. What about this guy? This is minus 3 kilojoule per kg. Fine. You can see this is minus 3. You can use this also, is equal to 75 into 10 cube kilowatts. Okay. Now this is in kilojoule per kg. So this has to be in kilowatts. Now if you simplify this, you will get M dot S in kgs per second actually. Okay. So this is M dot S in kgs per second because the units are set accordingly. So whatever the answer you get, you are going to get in kgs per second. And what are the units they are asking in the question? They are also asking in kgs per second. Good. Okay. So they are asking in kgs per second. Let us do this calculation. That's it. Okay. So now subtract this from 2770.9. 2770.9. So this value into 0.7. Into 0.7 actually. Okay, so this is the value 670.42. Now see here, even if you neglect this pump work is only 3 kilojoule per kg. Even if you don't subtract this 3 from this 670, you'll have 5. Still you have 667. So value doesn't change. Did you understand now why I am neglecting the pump works when I am doing some questions? Because even if you don't subtract 3 from this, the answer remains 667, and 667 doesn't change the calculation much actually. Okay, so anyway, here we are subtracting. So 667.42. So this value is 667.42. W net 667.42 kilojoule per kg. Now just divide this quantity, reciprocate this and multiply 75,000. That's it. Okay, so 112.37. 112.37 kgs per second is the 78.1 is coming. 112.37 I got. Nitin, you are getting 78.1 somewhere. What is the answer, guys? Did you all do the calculation along with me? 112, correct? Yeah, something close to 112.4 or 112.37 is what you can say. Okay, this question you can see we have included the concept of isentropic efficiency of the turbine so that you can understand few things. That's it. Okay, did you understand? It's not a very lengthy question, it's a conceptually simple question, but this calculations has to be done little carefully. That's it. Okay, if you do calculations slightly carefully, things are on the right track for you. Okay, fine. Yes, table 1.77. Yeah, something close to 112 is good enough. Okay, yeah. So let's see now. Okay, fine. So these are the two questions I think we can work out. Now let's go to the next topics of today, which is like feed water heaters. So let us see here, feed water heaters. So what are these feed water heaters? As the name it tells you, this device will actually heat the feed water. That's it. Okay, so devices used for, maybe the answer may sound like something joke, but it's actually the correct. Okay, so device, a device that heats the feed water. That's it. Okay, that heats the feed water. This is sometimes also called a regenerator, also called as regenerator, or feed water heater sometimes. Now let us see what is this purpose of feed water heating. Why you have to do heating? Why you want to do heating of some feed water? Feed water is nothing but water which is going into the boiler, correct? So that's called feed, actually feeding into the boiler. So why you have to heat that? That's the main point here. Look, normally if you take this Rankine cycle, TS, this is how you have the cycle. Okay, so you can see this is like states 1, 2, 3 and 4. Clear? So you have state 4. Now of course, because of not drawing to scale, this diagram looks like this, but actually this T2 and T3, if you compare, this will be very much large. Okay, means let's say if T1 is at atmospheric conditions and T2 is also at atmospheric conditions, because isentropic compression to pump doesn't change the temperature of the fluid much actually. Okay, so it just increases 1 or 2 degrees Celsius. But let's say if this is some 35 degrees Celsius and this is some maybe some 700 or 800 degrees Celsius, this gap between these two is very large, and practically this part of heat addition which you are doing, you can see this part of heat addition which you are doing here is at low temperature. So this part is actually heat addition at low temperature, relatively low temperature. Okay, so you can say heat addition at relatively low temperature. So because of this process 2 to, let's say for example if this point is 2 dash, okay, so because of this process 2 to 2 dash, the total mean average of heat addition will actually decrease. Okay, means basically it is, there is some particular value of mean temperature of heat addition. If you can somehow eliminate or basically reduce the amount of heating in this region by external heat source, then definitely mean temperature of heat addition gets increased. Did you understand? Means let's suppose somehow instead of starting heating from this point, if you start heating from this point, then definitely your mean temperature of heat addition will increase. Yes or no? Because this heat addition at low temperature is getting eliminated. Correct? Can you understand the logic? One more way to increase efficiency definitely is regeneration, but I'm just trying to give you some hint. Instead of starting this heating at this point too, somehow by some reason which is not known to you, if you can bring this fluid from this point to this point, and if you start heating from this point, then definitely mean temperature of heat addition will actually increase. Yes, can you all agree with this point? Yes or no? Correct. So if you start heat addition from this point, then efficiency gets increased because of increase in the mean temperature of heat addition. Now your job is how to heat this point, or how to bring this point to this particular point which I am noting here. That is done with the help of feed water heaters actually. Okay, so this feed water heaters is actually practically the devices which increase the temperature of the feed before entering the boiler. Okay, now if you see these feed water heaters, they are nothing but heat exchangers again. So feed water heaters are nothing but heat exchangers, normally counterflow heat because of high effectiveness. Okay, so I think Sandeep sir might have taught you in heat transfer. So normally for the same temperature range of operation, generally counterflows offer high effectiveness. Okay, because at the initial point the temperature difference will be large and heat transfer gets effectively happening. Okay, so anyway, feed water heaters are heat exchangers. Now there are two types in this: open type feed water heaters. Normally this is called FWH. Okay, feed water heater, and closed feed water heater. Closed feed water heater. The main difference in the principle of operation is here in heat exchanger, both the fluids means both the hot water and cold water, means steam and cold water, mix each other. Physically they get in contact, they get in touch with each other and they mix. Like it's like, let's suppose you are going for bathing, pouring hot water in cold water, so that heat transfer happens direct because of direct contact with the fluid. Okay, and in this case of closed feed waters, fluids do not mix each other directly. Fluids doesn't come in direct contact with each other. Fluids doesn't come in contact with each other. So fluids doesn't come in contact with each other actually. Clear? So they do not come in contact with each other. Now let's see in case of open feed water heaters how we actually heat the fluid. Okay, practically how it is expected to done is, if you have a turbine like this, okay, if you have a turbine like this, now let's see steam is flowing into this turbine. Okay, you have pump here, you have the condenser combination also. There is a condenser like this, condenser. Now let's see if there is a turbine like this T, what you generally expect is, after coming out of this pump, the fluid should travel like this and then enter into boiler. This is what the theoretical idea was. Means you have to construct, such a device where fluid, once it comes out of this pump, this fluid, when it's crossing this point, it gains heat from this hot gas, because in turbine completely hot gas, this steam is flowing in. So this fluid which is circulating in this tube will actually get heat from this turbine, or basically from the hot gases flowing in the turbine, and before entering the boiler, the temperature of this fluid will be raised from this point to this point because of this heating. But practically creating such a device means inside the turbine going for a tubing is very complicated. Okay, so practically manufacturing point of view, it's very difficult. And also turbine blades operation, because continuously this turbine blades rotate at very high velocities, so it's not possibly it's not possible for us to keep a passage like this inside the fluid. So in practical cases, what we do is, we will take out some steam from the turbine, which is called feeding or feeder steam, or normally called bleeding actually. So we will take out this steam and try to heat this water before it goes to the boiler actually. Okay, so let's see how this concept of regeneration is actually working out. Clear? Try to understand. I'm going to generate the block diagram and also TS simultaneously, so please be careful. Okay, first TS. Okay, so TS, and you have a graph. You know, we have one condenser pressure, P condenser, and also you know you have boiler. Okay, so this is boiler, and actual cycle that you have here is normal cycle. First I'm drawing the actual cycle. We have pump, then you have some boiler, plus superheater, of course. Okay, plus superheater. Normally we have understood we have to superheat the steam, superheater. Then there is some turbine, turbine, which actually generates some work output, and you also have a condenser practically. Okay, so you also have a condenser like this, condenser. Now these are the normal static devices which you have actually. Okay, so which you have, you can see normally it goes from pump, then this will take you to the boiler, then from boiler it comes into the turbine, then from turbine it enters the condenser, and from condenser this will enter the pump actually. So this is the actual cycle which is known to you, and you also know the corresponding TS diagram. Okay, you also know how to draw the TS diagram normally, which we are drawing for now. Now in this case of feed water heating, what you will do, you don't want to heat the fluid in this part, somehow you want to take this point from 2 to 2 dash without external heating, correct? So for that purpose of taking the point from this 2 to this A, let us say for example if this point is A, to take this point from 2 to A without externally heating, we will use the heat in the turbine. How we are going to use that heat? Actually proposed model is this, but because of modeling manufacturing constraints, what we will do, we will take out some steam from this turbine actually. Okay, so we will take out some steam from this turbine and we will send it into something which is called feed water heater. This device is called feed water heater. Let us say feed water heater, for example, feed water heater. Okay, now if this is feed water heater, just try to understand this. I am trying to tell you, now to this feed water heater, definitely the fluid which is coming out of condenser should go inside this, yes or no? Because this fluid which is actually you're heating here is nothing but coming out of condenser, and pump is actually pumping it. If you want to take this temperature from 2 to A directly, instead of directly sending this condenser into pump, because there is nothing heating here, before sending into this pump, you want to heat this fluid. Okay, so if you want to heat this fluid, this condenser outlet, instead of directly going to this pump, first it should go into this heater and the fluid should get hot. Understood? So if I connect this like this, if I connect this like this, actually there is one complication here from fluid mechanics point of view. If you observe, normally the stream which is coming out of the turbine will be at some pressure, P intermediate, let us say. Okay, so this is P boiler, so this steam, this turbine will make this steam operate from P boiler to P condenser, means you know that expansion actually happens from this point to this point actually, like this. Okay, so this is state 3 normally in our nomenclature. Okay, let's say for example from here to here, but the pressure which the fluid which is coming out of the condenser will be at very low pressure, correct? This intermediate pressures will be somewhere between this boiler and condenser, because you're trying to take steam out of the turbine in some between the complete expansion. So this condenser pressure will be not equal to P intermediate, correct? Understood? Yes or no? Can you all understand? This P condenser will not be equal to P intermediate, because this P intermediate is the pressure of the steam which is bled out from this turbine at some location in between complete expansion. Means let's say for example somewhere here, somewhere at this location, if I am taking out this, you know, there is one more pressure line. This is P intermediate, for example. Okay, so this is P intermediate, then definitely this P intermediate is more than this P condenser. Okay, now if you have for example open feed water heater, if you have open feed water heater, if fluids are trying to mix each other, if this fluid is having different pressure than this, then definitely this fluid cannot mix effectively with this fluid. Yes or no? Try to understand the logic here. This is P condenser, but this is P intermediate. If these two pressures are clearly different, then in case of open feed water heating, definitely this fluid cannot enter effectively into this feed water heater. Yes or no? Can you understand? Come on, type in the chat box quick. Simple logics, guys. Just understand. Just basic thermodynamics. Very basic points. Okay. Because clearly this fluid is at high pressure and this fluid feels difficult to enter this feed water heater. Now, if you want to send this fluid freely into this, means if you want to send this fluid effectively into this feed water heater, you should increase this pressure of the liquid which is coming from condenser to P intermediate, okay, because both of them has to be at P intermediate to mix directly very effectively. So that means if you want to raise the temperature of the liquid, because in condenser it's almost like this state, so outlet of the condenser, if you see from condenser outlet, if you want to increase the pressure from P condenser to P intermediate, what you should do, you need one device here. What is that device? The device which increases the pressure of the liquid. Come on, tell me. You need a pump, correct? So we need pump. Low power pump laga denge. Yes, correct. We should put a low pressure pump here. Okay, so we should go for a low pressure pump in general. So there is one low pressure pump, which actually the job of this pump is to raise this pressure from P condenser to P inlet. So there is a pump here, pump 1 let us say, and this is pump 2 for example. Now these two gets mixed up in this open feed water heater, and the outlet from this feed water heater is sent into this pump for feeding it continuously into the boiler. That's it. This is the modification in the cycle. Clear? So this is the story with the case of open feed water heater. Clearly the condenser outlet has to be increased to P intermediate because with the help of a pump, and the fluid when it goes in, because of mixing, this point 2 will get heated to somewhere, some other location, and that fluid will be sent into the pump, and pump directly feeds it to boiler by raising it to, from this pump will actually raise from P intermediate to P boiler. This pump will raise from condenser to P intermediate. Clear to all of you? Is this diagram clear to each and everyone now? Did you understand? We'll see how to draw TS, but first of all physical construction. Did you understand how we are physically constructing this diagram actually? Clear? Okay, I hope you all understood the effect of this feed water heaters now. Okay, now let's see how to draw the TS. That's the main story. Okay, now let's see. Okay, this point need not be exactly here, maybe somewhere here also, doesn't matter. Okay, so this point may go something like this. Okay, and this point here may not be here. Now let's see what we have. This is inlet to the turbine, and at this point you are taking out some steam actually. Okay, and here it's linked. So now try to understand here. Whatever the fluid which is coming out of the condenser, whatever the fluid that is coming out of the condenser, this pump is raising the pressure of the fluid coming from condenser to P intermediate. So the pump 2 is raising the fluid from this location to this location. Okay, I hope you can understand clearly. So this is, if you call this point 1, this is 2, and actually the work done by 1 to 2 is because of this pump 1 actually. Understood? Clear? So please claim it out regarding GATE 2025. How many ranks are sufficient for PSUs? Yeah, normally depends upon the PSU like you are aiming for, and again every year depending upon PSU rankings and all, you know, safe side I would say is something below 300 or 200. Yes. Okay, best, like if I want to talk in terms of marks, make sure you'll have somewhere in between 65 to 70 marks. That could definitely help you. Okay Prashant, fine, try to have some 65 to 70 marks somewhere in between. Definitely you can land yourself in PSUs. Okay, now let's see here. So 1 to 2 is basically this point coming from condenser to raise into feed water heater. Also into this feed water heater there are two inlets. One is this pump, one is bleeding from the turbine. Okay, so now if you take out steam at this point, in feed water heater what happens? This fluid which is here, because this feed water heater operates at some constant temperature which is nothing but P intermediate. Okay, so this fluid once it enters at constant pressure, heating of the liquid water happens. Yes or no? Whatever the liquid water which is coming through this condenser and this pump, that liquid water will get heated from state 2 to some other state which is here. Okay, and also by the time if you want to send this open feed water, this outlet of this feed water heater into pump, definitely the steam which is coming here inside should get converted completely to liquid. Clear? Try to understand here. If you want to send this mixture into this pump, the inlet to the pump should be made liquid definitely. That means the heat transfer in these two should be in such a situation, this complete steam or this steam should completely get converted to liquid actually. Means this is steam which you are taking out here. The steam, because of losing heat at constant pressure, it traces along this path, and this steam will end up at this state, and also the water which is coming from the pump, that will also get heated up and it will land at this state. Understood? So clearly this is the point of equilibrium of the two states. Understood? See, this water which is coming out of this pump will get heated up to the saturated liquid. Also clearly this is steam which is coming out, because if you want to send it inside the pump, there should not be any vapor content here. So clearly complete vapor should get converted to liquid. So this is steam which is taken out here, that steam completely will also get converted to vapor. That's how these two lines will meet at this point. Understood? Clear? So is it clear to all of you? Did you understand how this point is getting generated in this TS? Yes or no? Please type in the chat box. Clear? If you want to send this steam into the pump again, because this is actually steam, if you want to send this steam into the pump, the heat transfer inside this should be in such a way that steam gets completely converted to liquid. That's why these 2 points are meeting at this location, because the final outcome is at equilibrium. Okay, that's it. Okay, now once it comes here, then this pump 2 will raise this from intermediate to P boiler. So clearly you can see this state will again raise this from here to here. Okay, if this state is 3, if this state is 4, then after that boiler takes care then. Okay, so boiler will do this heat addition of this. This is 5, maybe this is 6, and this is 7. That's it. Clear? So let's say if out of the total, let's say for example, if this is 1, total 1 unit, 1 kg per second of steam is flowing, out of which you have taken out m dot kgs per second, then in this circuit it is 1 minus m dot. Because of mass conservation, if 1 kg is coming, 1 kg per second is coming in, if this is m dot, then this should be definitely 1 minus m dot. So here it is 1, here it is m dot, here and here in this part it is 1 minus m dot clearly, and again at this point both of them get mixed, and in this circuit you again have m dot, I mean 1 actually, it becomes total. Clear? It's simple mass conservation, just observing the devices, that's it, nothing big at all. Clear? Just by looking at the physical construction of this device, just try to generate the TS. Now once you generate TS, doing thermodynamic analysis and calculating efficiencies, all these things you can do very well. But first of all, is this construction clear to all of you? From this diagram, how you are able to generate this TS? Is this clear? Because many people mug up, they write, okay, like this one, again put one more loop, no need of mugging up. Okay, you can understand the logic from this particular small circuit. Okay, fine. Now let us do similarly. First let us do the thermodynamic analysis, then I'll give you the TS for closed feed water heaters. Okay, so first let us do the thermodynamic analysis for this cycle. Thermodynamic analysis. Clear? So let's see, let us do this thermodynamic analysis. So first let us do the analysis for feed water heater. Okay, so if you have this feed water heater, open feed water heater. Now let's say there is some outlet which is coming like this. There are 2 inlets. One is this steam and another is at this pump which is coming at. Okay, so you can see this is steam which is blended up. So steam, and here this is water which is coming here. Okay, and of course this is already, so I don't have enough time to complete ATD from fast track. So can you tell me very important 1-2 topics where I can score at least 2 to 3 marks? No, I cannot say, because even if you analyze previous year papers, there are questions from each and every topic, Namit. Clear? But definitely, yeah, again I cannot say, because the concepts are same all over. It's like equally important. There are situations where from ATD there are 6 to 8 marks, such that one question is coming from each and every chapter. Like one question from gas power cycles, one from vapor power, one from this IC engines, one from refrigeration and air conditioning. There are situations. Okay, so better you focus, because anyhow I think only 2 hours a day, and that too I think hardly 12 classes we have. Clear? I think not even 11 classes, I guess. Okay, Namit. Even if you solve PYQs of this subject, you can clearly see there is no much very particular topics actually. Okay, fine. So anyway, now if you see, what are the enthalpies at this points? If this is 1, if this is m dot, and this is 1 minus m dot, clearly, because you see in this circuit, in this small part, if this is m dot, this 1 minus m dot will flow to this remaining part, and both of them gets mixed again. Okay, so this is 1 minus m dot, and this is 1 actually. Now let us see, if you compare this with that diagram, this is state at which the enthalpy at this point is H6, correct? And what about at the condenser outlet? At the condenser outlet it is 1, after pump it is 2. So this enthalpy is actually H2 at this point. And clearly at this location the enthalpy is, okay, mass flow rate is 1 kg per second, but what is the enthalpy? This is after exit from the feed water. So H3, 3 is the enthalpy at this state. Means clearly you can see here the enthalpy is H3, here the enthalpy of the steam which is coming in is H6, here this enthalpy is H2. That's it. Okay, because these are the numbers we have kept, and we know corresponding points. If you put this enthalpy is coming out at H6, because when this steam is at an enthalpy of H6, we are bleeding it out. Okay, so it is H6. After this pump compression, this liquid is at an enthalpy of H2. So after this pump compression, this enthalpy is at a H2, and after mixing of the feed water heater, these two are coming and making a contact or equilibrium at H3. Okay, so that's H3 actually. So this is the equation. So if you see, H3 is equal to, because if you apply energy conservation, clearly you know Q dot for feed water heater, if you see, if you apply del Q minus del W is equal to change in kinetic energy plus change in potential energy plus delta H. Okay, and clearly these heaters are insulated because you don't want this heat to lose out. You want this complete heat only to heat this water. Okay, so you don't want any heat loss from this open feed water heater. This is 0. And clearly this feed water heater do not generate any work, and if you neglect these combinations, then definitely dH is equal to 0. That means enthalpy coming in should be equal to enthalpy leaving out actually in this feed water heaters. Okay, so if you equate that, then H in, what is H in? M dot into H6 plus 1 minus M dot into H2 should be equal to 1 into H3. So this is the energy conservation equation clearly. Okay, normally sometimes using this equation they'll give you some questions. Okay, now let us see what are the other things we can talk about. W net is equal to, now let us see, in the turbine, normally this is the turbine which you are using for expansion. The mass flow in the turbine from this point to this point is 1, and the mass flow from this point to this point is 1 minus m dot. Yes or no? From 6 to 7, the mass which is flowing in the turbine is only 1 minus m dot, because m dot you have already taken out from this turbine. Okay, so therefore this W net is equal to work interaction in 5 to 6, work interaction in the process 5 to 6 plus work interaction in the process 6 to 7 minus 2 pumps a day, 1 to 2 and also 3 to 4. Okay, so therefore you have 2 pumps, so W 1 to 2 minus W 3 to 4. So these are 2 pumps corresponding to P pump 1, pump 2. This is expansion in stage 1 and also the second stage. So now if you see, from 5 to 6, if you take total mass flow in the circuit as 1, this is 1, so H5 minus H6 directly, H5 minus H6 plus from 6 to 7, the mass which is flowing in the circuit is only 1 minus m dot. So 1 minus m dot times H6 minus H7 minus 1 to 2. So W 1 to 2. Again in this 1 to 2 is also having the same mass flow which is 1 minus m dot, 1 to 2 actually. So you can see this 1 minus m dot into H2 minus H1, H2 minus H1 minus W 3 to 4. So work interaction in 3 to 4 is nothing but this, again here the total mass is again 1 unit, so H4 minus H3, that's it directly. So H4 minus H3. So this is the expression for calculating total net work output. Okay, so M in mass conservation of energy, correct no? Correct, because this is m dot. No, look, if total mass flow in the circuit is 1 and if you are taking out m dot, okay, so you see here Before entering the turbine, the total mass is 1 kg per second. That's what I have taken. Clear? So out of that 1 kg per second, I am taking out m dot. Maybe m dot is some 0.7, 0.8, something like that. Okay? Or you can see if this is m dot, this is x times of m dot, 0 less than x less than 1. Clear? Understood? If I take this example, for example, this has m dot, then this should be x times of m dot, where x is in between 0 and 1. The remaining factor will pass through this condenser. Okay? Anything is fine, just you have to substitute accordingly. That's it. Okay? By this time you know how to write the expressions for work generation and work generation and also heat added, all this stuff. Okay? So anyway, I'm just using this one for easiness in the calculation. That's it. So this is what you have. And what about heat supplied? Heat supplied is equal to 1 is already there. So boiler is heating the system from 4 to 5 actually. So H5 minus H4. H5 minus H4. If you have not done regeneration, this boiler heating should start at this point, or maybe at this point. You can say this boiler heating should start at this point. Okay, because if you continue this isentropic expansion vertically onto this pressure, it will end at this point. So because of eliminating heat addition at this range, you are able to increase the mean temperature of heat addition. That's how your thermal efficiency increases, but clearly your net work output will decrease. Okay, because of course, even if you neglect this small pump work, but because of bleeding out m dot from this turbine, clearly this work falls. Okay, because this pump won't consume much energy actually, practically speaking, but since you are taking out some mass from the turbine, the amount of work is actually reduced. Clear? So this is how you have Qs. So therefore, if you want to calculate thermal efficiency, you can just divide these two quantities. Thermal efficiency is equal to W net divided by Qs. This formulas I have done by assuming let total mass flow rate in the boiler is 1 kg per second. That's what my assumption. That's what I have written. 1 minus m dot, all these things. Okay. Feed water heater is not heating, sir. It is heating, na? If feed water heater is not heating, then how your temperature is going from 2 to 3? See, if this heater is not heating this feed, then definitely how this is coming from H2 to H3? It is heating, no? That's why we are even writing this energy analysis. Clear? This del Q is equal to 0 is basically for heat interaction. Okay. Guys, look, I'll tell you something. First law of thermodynamics. That's why I was revising the things. See here. If this is your control volume, if you are writing Q minus W is equal to change in energy of the system, maybe kinetic, potential, enthalpies, whatever, you can see this is delta E of the system. This Q and W are the locations where it is crossing. Okay. If energy is going in and energy is going out, you remember I was talking about energy in minus energy out is equal to change in energy rate of the system. Okay. So these are at the boundaries of the control surface. Okay. So if you take this feed water heater, heat won't come outside this feed water heater. Okay. Internally they mix each other. Clear? Did you understand? Heat will not leak from the feed water heater. Clear? Because complete steam, the heat what is available with complete steam, that should mix with water, and that should get transferred to water. Clear? There is nothing which is crossing the controlled surface. Bleed steam is at high temperature and heating water coming from condenser. Yes, exactly. Vivek, did you understand? No. If you have doubt, you tell me. I'll just explain you, because it's not like just moving forward, but getting the things cleared. Any doubt in this point? Got it? Okay. Yeah. Fine. So this is how you can calculate this thermal efficiency. So clearly, because of increase in mean temperature of heat addition, thermal efficiency will increase. Okay. So this is the simple analysis you can see, and this is the construction of cycle from this TS diagram. Okay. Now let us see what are the effects of reheating. Okay. So what are the effects of this reheating? Just a minute. This need not be there. Okay. So see here, effects of regeneration. effects of regeneration. Effects of regeneration. So first, let us start from like the previous cases. Now, W net. Come on, tell me what happens to W net? Net work output. Increases or decreases? See this diagram and try to tell me what happens to net work output here. In this case, net work output, will it increase or decrease? See this W net, it will increase or decrease? I think I should write capital W, okay, better. Decreases. See why? I'll tell you. If there is no regeneration, actual work produced would be H5 minus H6. Oh, sorry, what are they? H5 minus H7 directly. Okay, so H5 minus H7. This is the work which is produced without regeneration. If you do regeneration, you have H5 minus H6 plus 1 minus m dot H6 minus H7. Of course, even pump works are also there. Minus 2 quantities are there, but if you neglect that, okay. So now if you see this term, I can adjust it as 1 minus H6 plus 1 into H6 minus H7. I can do this, correct? This is the actual without regeneration. Without regen. This is turbine work without regeneration. This is with regeneration. With regeneration. With regeneration. Now tell me, what's happening to your work? Net work output. Look, see guys, if there is no regeneration, I would have expanded the complete steam from H5 to H7 directly, okay. But because of regeneration, I am taking out some mass outside, okay. So for this part of the expansion, you don't have the complete mass available. You have only 1 minus m dot. Understood? So that's why in this analysis, you can see clearly this 1 and 1 minus m dot, clearly this is large, okay, and 1 minus m dot is definitely less than 1. So what happens to your work output? Net work output decreases, okay, because you are bleeding the steam out. You are not allowing the complete mass to expand and do work in the turbine. Understood? You are taking out some mass. Clear? It decreases. Yes, it should decrease. Okay. Now, what happens to QS? QS. If there is no reheating, you would have heated this substance complete mass from state 4 to from this state. Let us say, for example, if this is state 8. Okay. You would have heated the mass from state 8 to state 5. But now, because of regeneration, instead of starting heating at 8, you are starting to heat at 0.4. That's it. So what's happening to heat added? QS. What happens to QS? Actually decreases. Okay, so QS also decreases. And what happens to thermal efficiency? Increases, as I was telling since day 1. So this increases because of increase in mean temperature of heat addition, TH mean. Okay, so this is because of TH mean actually. Clear? So this is TH mean. Now fourth, dryness fraction at condenser. What happens to dryness fraction at condenser? Most important point. Dryness fraction at condenser outlet. Will it increase or decrease? What happens to dryness fraction at condenser? Same, correct? It won't change. It's not increasing nor decreasing. It will same, because even if you expand complete steam or only some part, you will expand only to the same point. Okay, so therefore this dryness fraction at turbine exit is same, remains same. Remains same. 5. Specific steam consumption. of the plant. Specific guys, is it fine now? Guys, is it fine now? Am I audible? Now clear. Okay, thank God. Lucky. Just a minute. Let me pop out this chart and yes. 1 minute. Let me pop out this. Okay. Yes. Fine. Okay. So let's continue. So specific steam consumption. What happens to this specific steam consumption? So clearly, you know, W net is actually decreasing. Okay. So if W net is decreasing, then what happens to specific steam consumption? Please tell me. Specific steam consumption. You know, specific steam consumption is inversely proportional to W net, correct? So if W net is decreasing, what happens to SSE? This will increase, correct? So this increases. I want to tell one more point. Load on condenser. Load on condenser. Normally, if you see, the main job of condenser is to remove heat. Okay, so heat rejection is equal to m dot times H7 minus H1 in actual case. Okay, so total mass flow rate 1 into H7 minus H1. If there is no regeneration, it would have been H7 minus H1. But now because of this is without regen. Without regen. This is QR. Okay, so capital Q dot R. Now with regeneration, you can see with regen, your Q dot R is going to be 1 minus m dot H7 minus H1, correct? So what's going to happen on load on condenser? This condenser load will increase or decrease. Means the amount of heat the condenser has to remove will increase or decrease. Come on, type in the chat box. What should be this value compared to this? It should increase or decrease. Load on condenser means the amount of heat removed from the condenser or removed from this working fluid in the condenser will decrease, correct? So this quantity load on condenser decreases. And I would also tell to one like to say 1.7 back work ratio. Back work ratio, BWR. Come on, tell me. Back work ratio is nothing but pump work divided by turbine work. Okay, pump work divided by turbine work. Here definitely because of these two pumps, pump work is increasing, but turbine work is actually decreasing. Okay, so turbine work is decreasing. So clearly, if turbine work is decreasing and pump work is increasing, what happens to your back work ratio? Actually, this will increase. Okay, so back work ratio increases. Clear? Because WP by WT is what you have here. So voice cut away. Is it? My voice is getting, you know, chopped off. Is the voice fine? Okay. Come on, type in the chat box quickly. Is the voice fine? No, sir, it is okay. Okay, fine. So these are important points because of regeneration. Clear? Okay, so all these points which you might have maybe remembered in previous cases, but now you need not remember this. Everything can be understood from one single analysis and also from one single diagram actually. Okay, so constructing this. Clear to all? Now the only thing before I start this gas power cycles, before I start gas power cycles, only one thing that I want to tell. This closed feed water heaters. What happens with closed feed water heaters? In case of closed feed water heaters, since both of these guys do not mix each other, the main thing is there is only one thing which changes in the circuit. See here. Okay, so let's see. There is a boiler plus superheater with open feed water, with closed feed water heater. With closed feed water heater, you can see with closed feed water heater. There is water heater like this, closed feed water heater. Now steam comes in at some P intermediate, and this liquid also comes. This liquid, or basically liquid from the condenser, also comes out. Okay, so this part is from the turbine. So somewhere here in between the turbine you are taking it out, then you have some inlet to the turbine actually, and also this condenser. You have the condenser, and this liquid is actually coming from the condenser. Okay, so this liquid actually comes from this condenser. This liquid is coming from the condenser. Now one thing here is, of course these two fluids, they do not mix each other, okay, mix inside. They just have indirect contact heat transfer, like how the tube and shell type of heat exchangers and all. So this is like closed feed water heater, and there is an indirect contact of fluid. Now if there is indirect contact, now what you do is, this pump, whatever the pump you have here, this pump can raise this pressure directly to boiler pressure, doesn't matter. Okay, and you can see, if you take this boiler plus superheater, boiler plus superheater in this case. Now let us see here, this pump will take it to the boiler, means if I generate the TS correspondingly, look, you will see this. If you have this TS, you have three pressures again, and boiler pressure, and also intermediate pressure. So this is P intermediate, this is P condenser, and this is P boiler actually. Now if you are taking out this steam like this at this part, maybe somewhere here, or maybe generally it's taken slightly on this higher end. So if you take this steam out, this is 1, this is 1 minus m dot. So clearly the steam which is coming out is at this point. Okay, so let's say this is the point actually. So this is constant pressure. Now since these two fluids do not mix each other, what happens is, there is one pump which takes this directly to this pressure, and for the rest of the fluid which is coming out, which is getting heated up, this pump can take this fluid directly here, and this heating between these two, you can see this part of heating, or this part of heating of the condenser fluid is happening because of this steam. Okay, so this is m dot and this is 1 minus m dot clearly. So this pump can directly raise this condenser outlet to directly this, you can see these 2 points. These 2 points are on the same P boiler line. They are on the same P boiler line actually. Okay, the reason for that is, okay, it's okay, fine. Okay, no more questions, no? Fine. See here, these 2 points, if you see, these 2 points will land up on same P boiler. Like in previous case, in case of open feed water heater, because of physical mixing, they both will come to some equilibrium position. But now only heat transfer happens. Okay, so heat transfer happens, and that heat transfer is responsible for taking off this condenser fluid. Okay, so you can see if I name them 1, 2, then this point is 3, maybe this is 4, then here complete mass flows into the boiler. So this is 5, 6, 7, if I take this, the main difference in case of closed feed water heater is these substances do not mix each other, so it's not mandatory they should meet at the same pressure and same temperature. Understood? So this pump will actually raise this water coming out of the condenser directly to the boiler pressure. So now if you see, it has a pump. You can see you have a pump like this, and this pump will have mass flow rate of only m dot, because this pump is already taking out this 1 minus m dot to already P boiler. Okay, now clearly you can see this will dedicate to boiler, and also this water which is coming like this. Okay, so see here, this water which is coming like this will get heated up, and this will also go to boiler like this. Okay, normally people connect them using a single line many times. You can see into this circuit you can connect like this. Okay, maybe something like this. Okay, so that it merges with this and both gets enter into the boiler actually at this point. Clear? So heat addition starts like this at this point. So this is this 1 minus m dot, which is already at the boiler pressure, because this pump directly raises this condenser to boiler 1 to 2 like this. Okay, so and this pump is responsible for raising this P intermediate again to this boiler, which you can see from 3 to 4. This pressure rise is between P intermediate to P boiler, but this 1 to 2 is from P condenser to P boiler, which you can see like this. And this is how you have the construction. And clearly, if this is the turbine, then definitely the outlet is this. Okay, so you can see this. Where is this? Yeah, this is how you have the circuit. Clear? You need not mug up anything. Okay, just try to understand the physics that's happening here, because here fluids are not in direct contact. So one pump is definitely sufficient to raise this from condenser to this boiler plus superheater directly, which I am also showing in the diagram. 1 to 2 is that. Clear? So 1 to 2, then 3 to 4. These two get mixed up at this point and they move up. Okay, we generally make sure that in this heat exchanger both come to certain equilibrium temperature, or heating happens until this steam becomes completely liquid. That's it. Okay, until this steam becomes complete liquid, heating happens, because to send it inside pump again you should convert it to liquid phase. Clear? That's it. Why we need CFEH if we can do regeneration by open feed water heater? Because normally if you see direct contact of liquids, okay, whenever you are trying to make direct contact of liquids, in case of second law point of view, what happens is irreversibility rate will be high. Normally I'm not discussing it because it's not even in GATE syllabus, normally not even in any of the syllabus. If you see direct mixing between for same temperature differences, this can create higher irreversibilities. You might have seen in 𝐂𝐬𝐧𝐤𝐬 chapter. Normally if you see mixing of two hot fluids and all, if you might have solved problems on that, normally in paid batches I'll teach in basic thermodynamics. But actually if you see, direct mixing can create high amount of irreversibility, because when fluids come in direct contact with each other, the temperature difference is felt very directly, and heat transfer between temperature difference is irreversible, and that is clearly felt in this case, direct mixing, in case of direct mixing. Okay, so that's why the irreversibility actually increases in this case, which practically do not happen only if heat is getting transferred from one point to another point. Okay, because in case of what happens is, in case of this closed feed water heaters, if you do second law analysis of cycles, second law of thermodynamics analysis of these cycles, you will find out normally in terms of exergy and entropies, all these things, direct mixing is actually more irreversible compared to indirect heat exchange. Okay, so that's why we generally go for this closed feed water heaters, and normally in industries you can see they go up to 8 feed water heaters. In open feed water heater more pumps are required, but pump work is not much. No, you can see pump work is, if you see the variations in pump works are almost neglected. It doesn't matter. Okay, Nitin? Clear? Pump works are very small, so it's okay to keep 1 or 2 pumps, but losing energy at the cost of irreversibility is more dangerous. Understood? So that's why. Okay, fine. Is this clear to all of you? Fine. Now, so again, if you want to calculate W net and all, you can do 1 into H5 minus H6 plus 1 minus m dot into H6 minus H7. QS is 1 into H4, H5 minus H4, pump works. 1 minus m dot into H2 minus H1 plus m dot into H4 minus H3. All these things you can write again as it is. Space constraint is there. Okay, space constraint is normally there in any industries, but in terms of efficiencies and all, this space constraints and all do not play much impact. Clear? That's why. So tomorrow HPCL give something guidance to crack. HPCL मैंने बहुत दिन पहले crack किया था. So just aptitude is again the game changer, because which I generally say, which I have seen in last exam also. Like normally technical questions are at that level, anyone can generally write the answers. Okay, because if you are preparing for GATE, technical questions बहुत आसान होता है, लेकिन aptitude में you know solving fast is the main key. Clear? You have to do the questions correctly and fast. That's the only thing I would say. Nikola Tesla. Okay, good name. Just be calm, be yourself, and try to attempt the questions. That's what I would like to say. All the best whoever is going for HPCL tomorrow. I wish you all a very good luck. And yeah, 85 questions in aptitude, I guess. Correct? Total 170 questions and 150 minutes. Yes, even I have written that. 85 questions in aptitude. Aptitude is there. Correct? Yes, 85 questions of apti and 85 questions of technical. Yes, even when I have written, that's it. 170 out of 170. My score was like 156, I think, at that time. Cutoff was 152 somewhere. But GD I got highest marks in India, 8 point something odd. That's the highest in India actually. Later I came to know, after joining HPCL, I came to know that's the highest in India. So anyway, just I have this HPCL cup I would like to show you, which still I keep with me. I'll just show you. This is the cup which is given by people. I generally keep my pens and all in this. Okay, so this is the cup when I was working in the office, people who gave me at that point. Yeah, I have this. Good. And I think I also have ID card. Okay, I'll just show you. Try to see you. During the training, this is, you can see the tag of HPCL. Maybe how I can show you this. Okay, I think you can see Hindustan Petroleum. I think with this focus you cannot see, but somehow you can do. Okay, so this is my ID card at that point during training. I still keep all these things. Okay, yeah. Technical में तो कर लेंगे, पर aptitude नहीं बनता उतना अच्छे से. नहीं, aptitude अच्छा बनना चाहिए अगर selection होना तो, ठीक है? क्योंकि technical I don't think many of the people cannot write. I mean, many of the people don't find any difficulty in technical, but like an aptitude में questions फटाफट से solve करना थोड़ा important है. Okay, I clearly remember even till today when I wrote aptitude, out of 85 my aptitude marks were 79. Yes, I still remember this. I lost only 6 questions. Out of that 6 questions, again 2 questions they gave add score because there was mistakes in questions. Rest of the marks I lost in technical because it's been so long since I have seen manufacturing, material science, these kind of subjects. So I lost few marks there. But apart from that, it's like this year there is negative marking. Then also there is negative marking. There is negative marking always. Okay. 0.33, 0.25 I guess, correct? 0.25 or 0.33 something. But it's okay. Yeah. Always attempt confidently. Be confident. That's it. You can do good. 0.25 or 0.33 I think. There is negative marking at that time. It's long back in 2021 somewhere. Okay. Fine. So anyway, let's continue. So what we are talking. So this is what about the story of feed water heating. Okay. Now, if you see regeneration, more the stages of regeneration, efficiency of Rankine keeps touching efficiency of Carnot, because you know ultimately the point of doing regeneration, all this stuff, is to increase the thermal efficiency. Okay, so 0.25, this is a negative marking. Okay, fine. So here you see this is thermal efficiency of the Rankine cycle. So and clearly if you keep on doing the regeneration stages, then that keeps on increasing the thermal efficiency of the things, and finally you will approach Carnot efficiency. Okay, so normally they can ask you if you keep on increasing number of stages of regeneration, because this I did not tell you in reheating, because practically I told you cannot keep on increasing the reheating stages. Okay, because after a certain point of reheating, what happens is the pressure difference in the turbine will be very small, so that you won't get much amount of work. Okay, so but in this case you can do that actually. Okay, yeah, you can keep on doing number of regenerations, and number of regenerations, number of feed water heaters, all these things, they depend upon the economical cost of the plant operation, and we can decide accordingly. So number of feed water heaters, they depend on economical conditions of the plant actually. Clear? So anyway, this is the point which I want to tell you actually. Clear? So with this I would like to close vapor power cycles. There's only one question I think we'll solve. What is the time, by the way? 5:35. Okay, we can solve one question maybe, and then we'll start gas power cycles. Okay, so let's see. Let us solve this question. Come on, I'm giving you some time. The specific enthalpy at state 6 is dash kilojoule per kg. Enter in integer. Okay, integer type, and 150 seconds I'm giving. Come on, start. Come on, enter the poll. Look, I'm hiding the poll. 150 seconds you have. Come on, solve this. A power plant working on a regenerative Rankine cycle with an open feed water heater H1. So 1 is this state, H1 is 2922, H5, this 5 is 273, and bleed to the feed water heater is 20% of the boiler steam generation rate. Means if this is 1 kg steam, for example, then this is 0.2 kg. That's what clearly. The specific enthalpy at state 6 is dash. So what is the specific enthalpy at this point? That's what you have. Come on, do this question. Come on, do this question. Actually, it's a nice question. H1 is given. You don't know what is H2. H5 is given, and you want to calculate what is H6. Do this. Come on, solve this question. Oh, sorry, something is happening here. Solve this question meanwhile. Come on, okay, fine. I'll also solve meanwhile along with you. So the specific enthalpy at state 6. Okay, so if you take this analysis for state 6, you see this is state 1 actually, and this is state 2. Now you can see the power plant working on a regenerative Rankine cycle with an open feed water heater, H1 is this, and bled to the feed water heater is 20% of the boiler steam generation rate actually here. Okay, and I think this is H2, guys. Okay, with an open feed water heater, H2. Please make this H2. Okay, otherwise I think it's not very convenient to solve this question. So please make it H2. So H2 is given. So clearly, you know, in this feed water heater, if you apply energy balance, we have 0.2 times H2 plus 0.8 times H5 is equal to H6. This is the simple equation that we have. So 0.2 into H2. So what about H2? 2922 plus 0.8 times of what is H5 actually? So H5 is 273 is equal to H6. So what about H6 actually in this case? So H6 is equal to certain kilojoule per kg actually. Okay, so we have certain kilojoule per kg. 0.2 into 0.2 into 2922 plus 0.2 into 2922 plus 0.8 into 273. 0.8 into 273. Oh, this should be 0.8 now. Let us see. 0.2 into 2922 plus 0.8 into 273. Okay, so this is what you have. So if you simplify this, the enthalpy is 802.8. Correct? So 802.8 kilojoule per kg is what you have. Yeah, 802.8. Correct? Yeah, 802.8 kilojoule per kg is the enthalpy at this feed water heating. Okay, so they'll ask you 1 mark questions and all based on this. Okay, I think these are the questions on Rankine cycle. Fine. Now let's go to gas power cycles. Clear? So is this clear to all of you till this point? Okay, are you all comfortable with vapor power cycles now? Concepts of reheating, regeneration. and understanding things. Yeah, 802.8 is correct answer. Okay. Now let's see this gas power cycles. So clearly this gas is the working fluid. Gas is the working fluid, and normally we take it air for our analysis. Okay, or normally in case of gas engines and all, turbine engines, we have the combustion gases. Okay, so combustion gases are the working fluids actually here. Okay, now the main thing is, instead of like why I am teaching IC engine cycle separately is, there the system is closed. Okay, we assume the system is closed and we do the analysis. But here in case of like if you take Brayton cycle or things like that, the system is open. Okay, so there is an open cycle that we generally deal with. Okay, now let's see what is this working fluid, and before going for these things, let us make certain assumptions which we work out. First and foremost assumption is like, again, air is treated as perfect gas. Treated as perfect gas actually here. Okay, so air is treated as perfect gas. Then after this, Cp, Cv, R values are taken at 25 degrees Celsius. Then in case of open flow devices, mass flow rate is same across all devices, means across the circuit, means there is nothing like mass is leaking out or something. So across the circuit, then yeah, compression and expansions are isentropic. Compressions and expansions are isentropic in ideal case. Okay, isentropic. Of course, you can see there is some devices like compressors and turbines which also have some isentropic efficiencies. Now first let us see the Carnot cycle, then Stirling and Ericsson. Carnot cycle. Okay, then if you want to see the physical construction, how Carnot is actually constructed, or just PV and TS is fine as of now because time is a bit short. So shall we go with PV and TS? Because how PV is coming, okay, it's okay, fine. I'll upload the document of a Carnot cycle, how Carnot cycle is getting, how we can physically generate a Carnot cycle. Okay, better, because anyhow in paid batches I have taught, so I'll take out a page from there and put it in the Telegram group. Fine. Okay, so just right now, as of now, because the time is a bit short, so I'm just working out the things. Clear? So if you go with PV diagram, we all know that the process runs between two isotherms. P and V. So if you draw two isotherms actually here, now clearly initially you'll have some heat addition, isothermal heat addition, which is like this, heat addition QH, and if this is temperature TH equal to constant and this is TL is equal to constant, then from this high temperature to low temperature you have a compression, adiabatic compression at a higher slope. Okay, so 1, 2, 3, this is isentropic expansion actually like this. Okay, PV and TS is fine. Okay, so this is the case. Then after you have heat rejection along this constant temperature, which is like QL across this TL, and then you will again do compression to take it to the same initial state adiabatically. Okay, so this is isentropic. Clear? So this is how we have the Carnot cycle. I told you clearly, normally the best way to do expansion is actually isothermal, and heat addition as per your second law is isothermal. So this isothermal process, after this, even though this isothermal expansion gives you larger work than adiabatic, you still go for adiabatic, because if you generate a cycle, this heat addition along isothermal and expansion also again isothermal, when you take it back, the net work is 0. Okay, you can't get in network output because the cycle closes with 0 volume. Clear? So that's why you have. Then clearly TS. If you plot with TS, because in Carnot cycle you might have seen in basic thermo, so I'm just going a bit quick. So TS, then this process 1 to 2 is at constant temperature isothermal. So you can see it's like a box, just like a box here. So this is state 1, state 2, state 3 and state 4 clearly. So this is heat addition at temperature TH, and this is TL actually. QH, QL, W out and W in is what you have here. Okay, and if you wish to do thermodynamic analysis, clearly you can see thermal efficiency 1 minus QR or QH, QL I think I have taken, QL by QH. So 1 minus, these two are isentropics, isentropic expansion and isentropic combustion actually. So now isothermal heat addition and isothermal heat rejection, they are reversible. So 1 minus QL is nothing but heat addition in this, which is TL into S3 minus S4 in magnitude divided with TH into S1 minus or S2 minus S1 clearly. But since S2 minus S1 is same as S3 minus S4, the reason is this is isentropic expansion, so S2 is same as S3, and this is isentropic compression, so S1 is same as S4. So clearly S3 minus S4 is same as S2 minus S1. Then definitely these two things gets cancelled. You have thermal efficiency of this cycle is 1 minus TL upon TH. Clear? So that's what you have here. So that's how we can generate the expression for thermal efficiency of a Carnot cycle, which we generally use in all the calculations across the cycles. सर मैं thermal portion में weak हूँ सर, कैसे strong करूँ, especially FM में ज़्यादा problem होता है. लेकिन FM के लिए पहले जो fundamentals होता है ना, first 4-5 chapters वो आना पड़ेगा. अगर 4-5 chapters में बहुत confident है तो बाकी सारे chapters सिर्फ applications होता है. Okay, but लेकिन in thermal is like again easy. Like in any subject, first 3-4 chapters are generally important. Okay, in thermal domain actually. Okay, so just try to have some grip on those topics. Clear? Now let us see, this is thermal efficiency 1 minus TL by TH. Now what is this Stirling and Ericsson cycles? Stirling, comma, Stirling cycle and Ericsson cycle. Now you can see both these cycles uses a regeneration concept. Uses a regeneration concept means that is they use regenerators. They use regenerators. Okay, normally the actual construction दोनों में efficiency सब इंजन के लिए है. Sorry, didn't get you. सब या फिर डीजल इंजन के लिए पता नहीं. I mean didn't get your doubt. Demo efficiency. What is demo efficiency? Didn't get. Sujay, so please elaborate your question. Okay, so now if you see what is the regenerator is basically in this, they absorb heat from working fluid, during some part of the cycle, and gives back same amount of work, some amount of energy. Okay, so same amount of energy, some part of they absorb energy. Okay, you can say energy, it can be in any form in general. So they absorb energy from working fluid during some part of the cycle and gives back same amount of energy to the working fluid, at some other part of the cycle, actually here. Okay, so these are called regenerators. So fluid mechanics की class कब से चलेगी? Over already. I myself have taken. Okay, so just go around some roughly 20-25 days back in the same channel you will find my videos. Okay, now let's see, this is what you have. Now the physical construction given by Stirling is actually very complicated. Okay, but if you try to model that, we use something called thermal regenerators, And for these thermal generators, what happens is the capacity, the heat capacity, means mass into specific heat combination, is very high for this regenerator substances. During some part of the cycle, they absorb gas from the working cycle, from the working fluid, and in some other part of the cycle, they actually give it back. Okay, so right now again, I'm not putting the physical construction because I'll just upload the document better. Okay, because anyhow I have it. I'm just going for PV and TS. In these two cycles, both in Stirling and Ericsson, cycles, they are reversible cycles, of course. Ericsson cycles, heat addition and heat rejection. Heat addition and heat rejection are isothermal. Okay, isothermal. Again, I'm not putting the physical construction, how physical construction is happening and all, how piston, cylinder movement, all these things. Normally, in case of Stirling cycle, you'll have two pistons, okay, and there will be regenerator in between. And depending upon the movement of the pistons, what happens is these two pistons move equally during the heat rejection and also heat transfer actually. Okay, and we'll see this compression and expansion means that affect the changes in the states of the gas to bring from TH to TL will be at constant volume. Okay, so just if you see PV for Stirling cycle, if you plot this PV diagram, P and V, clearly you have isothermal heat addition as I have told you. So this is 1 to 2, and from 2 to 3, for getting this temperature from TH, because this is TH is equal to constant, and similarly you have a compression which is TL is equal to constant, along TL is equal to constant. These are isotherms. Okay, now to bring this temperature of the working fluid from TH to TL, we will see the pistons actually move uniform, I mean both with uniform speed, so that the gap between them is remain same. So this temperature drop will be because of constant volume, and this is because of, okay, let me draw it how it looks actually, because this temperature has to be large. This is isothermal, 1 to 2, TH is equal to constant. Then you have constant volume 2 to 3, and this point 4 will be again along constant temperature, TL is equal to constant, and these guys are again constant volume. Okay, I would have given physical construction also if there is some time, but okay, in fast track anyhow the time is a bit short. 1, 2, 3, 4. Okay, so this is what you get: 1 to 2, 2 to 3, 3 to 4. Okay, and these are constant volume processes. So you can see these are actually not expansions and compressions, but that constant volume, the temperature of the system is brought from state 2 to state 3 by giving some amount of heat to a regenerator. Okay, and again at this point at the same volume, this temperature is brought from 4 to 1 by, look, if there is some substance which is taking heat, for example, okay, this is actually a regenerator. Now what happens, this regenerator takes heat from the gas during this process 2 to 3. Okay, so at constant volume, if heat is taken out, then definitely the internal energy keeps coming down. Okay, so 2 to 3, there is a temperature drop actually, I mean there is a pressure drop, and of course temperature also decreases from TH to TL. Now at this point 4, what happens, this system gives back its energy to the system, so that, sorry, at this constant volume, the pressure and temperature both increases for this particular system. Okay, so this is what you have PV for this Stirling cycle, and regeneration happens here between these two. So regeneration means heat transfer happens, means this during this process 2 to 3, this regenerator collects heat from the system, and during 4 to 1 it gives it back, so that it again raises from TL to TH actually here. Okay, so regeneration happens during this process. Now if you see a TS for this, TS, so you can see TS actually, TS, then 1 to 2 is your heat addition, 1 to 2, this is TH, for example this is the line of TH, This is the line of TH, and this is the line of TL, for example. TL, you can see carefully. This is TH here. Process 1 to 2. 1 to 2 actually here. Now, can anyone tell me this 2 to 3 is constant volume process clearly? So constant volume heat rejection has to be there, because during this part of the system is giving heat to its regenerator. So the temperature of the working fluid is decreasing at constant volume. If temperature is decreasing because of transfer of heat from working fluid to this regenerator, if you see ds is equal to del Q by T, because it is reversible, no entropy generation. Now you can understand one thing, this del Q is negative because heat is flowing from the system to this regenerator. So clearly entropy decreases and this cycle comes like this. Similarly, you can see if you connect this, we have 1, 2, 3, 4. So 1 to 2 is isothermal heat addition, like here you can see, and 2 to 3 it's basically 2 to 3 is actually this constant volume process. V is equal to constant, and this is TH is equal to constant, then TL is equal to constant. Then again during 4 to 1, when this substance is giving back its heat, then clearly you can see from 4 to 1 entropy will increase along with temperature. So from this point to this point, it's constant volume process. At constant volume temperature increases as well as entropy increases, because at 4 to 1 del Q is positive because this regenerator gives back its energy to the system actually. Okay, and regeneration happens between these two stages actually. So this is the regeneration stage. Okay, so that's how you have this. And clearly if you try to calculate the thermal efficiency of stirring, you will find out it is as per Carnot's curve. Heat additions are isothermal and temperature limits is same, TL, TH. So efficiency should be same as Carnot efficiency. So this is what you will get. Okay, same as Otto cycle but heat isothermal process. Yes, exactly. Okay, now if you see Ericsson cycle, what is the time? Okay, 4 minutes, fine. Let's see Ericsson cycle. Ericsson cycle, if you see, this is actually, I can show you the physical construction, it's a bit simple comparatively. If you have this as the regenerator, then if you have turbine, okay, so this is your turbine, and if you also have compressor, if you also have some compressor like this, then you can see fluid transfer happens in this way. Let's see if you don't connect these two, for example, how power is actually generated in this. Okay, so this can come like this, and just a minute, so you can connect this tube. Let's say this is a single tubes actually. I'm again showing only block diagrams. And just a minute, sorry, 1 minute, let me delete this. Then it's a single tube, of course. Let me draw a sketch here so you can see. This is how something it has. Okay, and clearly this high pressure gas will flow like this all over, and it comes into this. Okay, and heat transfer happens during this constant pressure. Heat transfer happens from here to here actually. Okay, so that's how some physical construction is there. But anyway, if you go into much details of physical constructions, you can see this is turbine, this is compressor, and these two are actually connected by this regenerator, okay, so that this produces some work output in the isothermal expansion, isothermal heat addition, and this is at work in the compression. And if you see PV versus TS, PV diagram, you can see PV. So you have isothermal heat addition, okay, so let's see, you have isothermal heat addition like this, state 1 to state 2, this is isothermal. Now clearly there is a constant pressure compression which actually takes place like this, okay, and then again you have heat rejection at this point, because and you have a constant pressure curve which closes this diagram like this, okay, so this is a constant pressure curve. I'm not elaborating these things because anyway in basic thermodynamics you might have seen, just drawing the plots 1, 2, 3 and also 4. So this is actually a heat addition, this is your heat addition Q, heat addition, let us say this is QH, and this is heat rejection. During compression, during compression temperature increases, but to keep this T constant, you will allow the heat to flow out, and regeneration happens in this way. Regeneration, okay. And similarly, if you go for TS, these two becomes straight lines, and this 1 to 4, 4 to 1 and 2 to 3, this becomes lines of constant pressure having slopes. And here also, if you see thermal efficiency of Ericsson is 1 minus TL by TH, again in this case also, and processes are heat addition and heat rejection are isothermal, heat addition and heat rejection are isothermal, and other processes are constant pressure processes, constant pressure processes actually, okay. So you have this constant pressure process, clear. So we can do thermodynamic analysis for all these cycles depending on constant isothermal, then constant pressure, all these points. So if you do, you will end up with Ericsson being 1 minus TL by TH. So this is in accordance to the Carnot's corollary, that if all reversible cycles are operating between same temperature limits with isothermal heat addition and isothermal heat rejection, then the thermal efficiencies of all these cycles is same, which you will see thermal efficiency of Ericsson is same as Stirling, is same as Carnot actually here in this case, okay. In the previous case I think I have taught, and both these concepts of both this Stirling and Ericsson, they use concepts of regeneration basically depending on the substance. Here also you can see in this cycle, because of isothermal heat addition, it comes to QH, okay. But at constant pressure, if heat is transferred from this at constant pressure, if heat is transferred from this substance to the regenerator, then definitely what happens at this point, volume keeps decreasing, okay, because temperature keeps falling, so volume keeps decreasing. At this temperature TL, what happens when you start to compress the gas again, its temperature clearly increases because of compression, temperature increases, but to keep this temperature heat rejection at constant temperature, we allow this heat to flow out. Again at this point, the substance takes energy from the regenerator, and at constant pressure, temperature and volume both increases from TL to TH, and also volume increases from V4 to V1, okay. So this is how physically this cycle is constructed. But anyway, you can go in much details. Of course, it's not exactly in the GATE syllabus, but still, if some of you are at ISRO or ESE prelims and all, it could be helpful to you, clear. So this is how we get the cycle. In case of Stirling, apart from isothermals, we have two constant volume processes. In case of Ericsson, we have two constant pressure processes. That's the difference in the construction, okay. So I think the time is up. We will stop here. We'll start Breton cycle tomorrow. We'll start analysis, then we have solved this question. Okay, fine. You can try this question actually if you have some idea from your previous knowledge of applied thermodynamics, okay. And in today's class, we have seen feed water heaters, then concept of regeneration. We have seen effects of regeneration, and also we have seen gas power cycles, this Carnot, Stirling and Ericsson cycles. Plus we have also solved some numericals. Okay, so these are the things that we have discussed in today's class. Okay, and if you have any doubts, you can ask me. Otherwise, this is the Telegram ID. If you wish to join, you can join here. Some doubts and all, you can ask me here if you have. Okay, so these are the things that we have done in today's class. In tomorrow's class, we will start with Barton cycle, and we'll see thermodynamic analysis of Barton cycle along with concepts of heating and regeneration. Okay, so right now, if you feel difficulty in understanding this circuits, okay, like let me just tell you this one, and also basically this understanding of regeneration, it's okay. Just now, please keep in mind it has two constant volumes and this has two constant pressures. That could help you out, okay, in exams and all. Clear? Okay, just you have to know the cycles. Okay, that's good. That could be better. If you have any doubts, you can ask me, or else it's fine. We can wind up the session actually. So that's it. Then we'll have one more class tomorrow before we have the weekly off. So tomorrow we'll see Barton cycle analysis. We'll try to, again, tomorrow is like one short session of Barton cycle, right? From starting to ending, we will try to do the things. Okay, so thank you all. We'll meet tomorrow at again 4 p.m. and we'll try to have some like one short session of Barton cycle. Okay, so thank you all. Thank you.